Question. I will read it once again. We want to recover the waste heat from the exhaust gas of a car using thermoelectric generator modules as shown in the figure. Figure is given here. An array N is equal to 24 TEG modules is installed on the exhaust of the car, and each module has N is equal to 98 thermocouples, each of which consist of P-type and N-type thermoelements. The exhaust gases flow through the TEG device, wherein one side of the module experiences the exhaust gases while the other side of the module experiences coolant flow. So these causes the hot and cold junction temperature of the module to be at 230 degrees Celsius and 50 degrees Celsius respectively. To maintain the junction temperature, the significant amount of heat should be absorbed um, at the hot junction and liberate at the cold junction, which is usually achieved by the heat sinks. So the material properties of the P-type and N-type thermo element are assumed to be similar as alpha P is equal to alpha minus alpha N is equal to 168 mu V per Kelvin, and rho P, the resistivity, this is conductivity, okay, is equal to rho N is equal to 1.5 times 10 to the power minus 3 ohm centimeter, and Kp is equal to Kn is equal to 1.18 times 10 to the power minus 2 Weber per centimeter Kelvin. The cross-sectional area of the leg length of the thermo element are An is equal to Ap is equal to 12 millimeter cube, and Ln is equal to Lp, that is a length, is equal to 4.6 millimeter respectively. So we have to find per 1 TEG module, compute the electric current of the voltage and maximum power output and maximum power efficiency. So for that, what we found, first we calculate the Z value, it will be alpha square by rho K. So substitute the values which is given here, you will get the answer 1.53 times 10 to the power minus 3 Kelvin inverse, and C times T bar is equal to, you will get the answer, the Z is times Tc plus Tb divided by alpha, then you will get the answer of Z T bar is equal to 0.633. Now you have to find that is rho L by A. You have to substitute, you will get the resistance value. For 1 TEG, current equation will be I is equal to alpha times Th minus Tc divided by R1 plus R. Substitute the values, or only you have to remember the mathematical formula and substitute the values here. And from there we have to calculate then W and eta. So this much we calculated last week. Okay. So this will be maximum power efficiency, that is eta. We got the answer 0.59. Similarly, maximum power output also, this is the value. Now this is for the whole system. Now per B question is for whole T. This is for one device. Now B question is for whole TEG system device. So for whole TEG device, what will happen? Maximum output Wn will be 24, right? 24 modules are there, so 24 times 7.493, it will be 179.8 watt. Now maximum that we already found eta value, that will be 0.051 eta will be 0.051. Now what you have to know? Eta maximum you have to calculate. Eta maximum is equal to 1 minus Tc divided by Th times 1 plus Zt bar, that is root of minus 1 divided by root of 1 plus Zt bar plus Tc divided by Th. Now you have to substitute the values here. So 1 minus 323 divided by 503 times root of 1 plus 0.633 divided by root of 1 plus 0.633. If you in this is plus 1, then plus 323 divided by 503. That answer you have to calculate, and please let me know what will be the answer. Then you have, from there you have to calculate total heat absorbed, that will be QH bar, that you can write Wn minus divided by eta maximum MP value. So how much you are getting here? 0.052 you will get here. So your answer will be 179.8 divided by 0.052. So the answer will be, I am writing here, 3525 watt. So please go through it first, all the session. This is the question. Okay, question is a little bit big, but you have to understand and apply the formulas. Next problem, today's first problem. Heat engine is operated between 700 degrees Celsius and 30 degrees Celsius. So heat engine, this one, okay. And it derives a heat pump which works between the 100. So heat pump also there work between the 100 degrees Celsius and 30 degrees Celsius. The efficiency and coefficient of performance of the heat engine and heat pump are half of the corresponding Carnot values. Calculate the amount of heat rejected by heat pump at 100 degrees Celsius, okay, when 100 kilojoule is absorbed by the heat engine at 700 degrees Celsius. So what are the parameters given here? We have to first draw the diagram first. So I'm considering heat engine here, and heat pump also working after that. Heat pump also there. Okay, now the temperature is T1 is equal to 973 Kelvin. Input and output temperature. So Q1 will be the heat, Q2 will be the heated, and T2 will be 303 Kelvin. Now here T3 will be 373 Kelvin. This output, okay. And here also we are giving as T4 is equal to 303 Kelvin. This is Q4 value, this is Q3 value. So we are making the diagram like this. And W you can write it as Q1 minus Q2. Now we have to see what are the parameters given. So T1 temperature is given 700 degrees Celsius. You can convert it into 973 Kelvin. Similarly, T2 is given 30 degrees Celsius, that will be 303 Kelvin. Then T3 is given, it is 100 degrees Celsius, so 373 Kelvin. And T4 is given, that is 30 degrees Celsius, you can just 303 Kelvin. Now efficiency, that eta actual efficiency will, you can give it as half of the eta max. Similarly, for a heat pump, COP actual value will be half of the COP maximum. So it's given in the question. Now Q1 is 100 kilojoule is given. You have to calculate Q3. So these are the things is given in the questions. Now for further you have to calculate what will be the efficiency maximum, half efficiency of actual. Then from there you have to calculate the Q2 value and work produced, total work produced by the engine also. So for that, first for a heat engine, eta maximum times T1 minus T2 divided by T1 is equal to, we can write as 973 minus 303 divided by 973. You will get the answer 0.6886. Okay, now eta actual, how much it will be? It will be half of the eta max. So that you can write it as half of 0.6886. So it will be 0.3443. Okay, now eta actual you can given as W1 by Q1. So that will be Q1 minus Q2 divided by Q1. So substitute those values. Eta actually it will be 0.3443 is equal to 100 minus Q2 divided by 100. From there you will get the value of Q2, it will be 65.57 kilojoule. Okay, now work produced by the engine, work W you can write as Q1 minus Q2. Q1 Q2 is already we found it, so it will be 100 minus 65.57, that it will be 34.43 kilojoule. So what you have to do, you have to just listen the question carefully and draw the diagram perfectly. Then from there you can easily calculate the value. You have to know the efficiency equation, work done equation for to solve this problem. Okay, so first go through the problem and try to solve it both. Now this we only found for heat engine. Now we have to do it for heat pump also. First we will go through this and we will go for the heat pump. Now what we do, we will go for heat pump also. So for heat pump, work supplied to the heat pump is equal to work produced by engine. Okay, so it will be Q3 minus Q4. You can write it as whatever the we got earlier, 34.43 kilojoule. Now COP value maximum will be, you can write T3 divided by T3 minus T4, that is 373 divided by 373 minus 303. So you'll get answer 5.3286. Okay, now COP actual value, how it will be? Half of COP maximum. So that you can write half of 5.3286, it will be 2.6643. Okay, now you know COP actual value, that COP actual you can convert like Q3 divided by Q3 minus Q4, that will be same as 2.6643. Now Q3 you can find it, see 2.6643 times Q3 minus Q4, already it's there, so 34.43. So that answer will be the value of Q3 that you have to find it. Okay, so this is the way to solve this problem. Now we will go to the next problem. A heat pump is used to maintain a conference room at 20 degrees Celsius when the surrounding temperature is 8 degrees Celsius. Calculate the power required to run the heat pump if COP is 4 and the heat loss from the room is 1200 kilojoule per minute. Okay, so this you have to solve. So what are the so let us draw the diagram. So heat pump. So Q2 will be atmospheric temp atmosphere that at 8 degrees Celsius, and the heat temperature changes to room temperature. It will be 20 degrees Celsius. This is value you can call it as Q1, and the input work done will be Q1 minus Q2. Okay, now T1 is given, that is 20 degrees Celsius. You can write 293 Kelvin. Similarly, T2 is given 9 degrees Celsius. So it will be 281 Kelvin. Now Q1 is given 1200 kilojoule per minute. So that you can write 1200 divided by 60. So 20 kilojoule per second. Okay, now heat pump deliver the heat to room from the atmosphere that is equal to the heat lost from the room. So heat lost from room is equal to heat to be delivered by heat pump. Now COP of pump will be Q1 divided by W, that you can write as 4 is equal to 20 divided by W. From there you will get the value of W is equal to 5 kilowatt. So this is a very easy problem. Just you have to know the logic from where the heat is coming and where is it coming. You have to equate that is lost and delivered to the system. You have to equate, then find the values. Now we will go for the next problem. A reversible heat engine operates between two reservoirs at temperature 727 degrees Celsius and 27 degrees Celsius. The heat engine drives a reversible refrigerator which working between reservoir at temperature of 27 degrees Celsius and minus 20 degrees Celsius. The heat absorbed by the engine is 2600 kilojoule and the net work output of the combined engine refrigerator plant is 500 kilojoule. Determine the heat transfer to the refrigerant and the net heat transfer to the reservoir at 27 degrees Celsius. So net heat transfer you have to calculate for this problem. So for that what you have to do, first you have to draw the diagram. So heat engine will be here. So the temperature is coming here. T1 is equal to 1000 Kelvin. Heat coming out. Okay, so this will be the diagram. Okay, so T1 you can write as 727 degrees Celsius, that will be 1000 Kelvin, and T2 will be 27 degrees Celsius, that is 300 Kelvin, and T4 will be minus 20 degrees Celsius, that is 253 Kelvin. Now T3 is 27 degrees Celsius, that is 300 Kelvin. W net is given, that is 500 kilojoule. Now Q1 is given 2600 kilojoule. You have to calculate Q4 how much. Similarly Q2 plus Q3 you have to calculate. Okay, now for this the eta value efficiency by Carnot cycle you can write T1 minus T2 divided by T1. So it will be 1000 minus 300 divided by 1000. So you can give it as a 0.7. Okay, now W1 will be eta times Q1. So Q1 value 0.7 times 2600. So it will be 1820 kilojoule. Okay, now W1 only same as Q1 minus Q2. So from there you will get Q2 value. It will be Q1 minus W. So that you can write it as 2600 minus 1820. So it will be 780 kilojoule. Okay, now W net you can write as 500 kilojoule. So it will be W1 minus W2. So from that W2 value you will get it 1820 minus 500. So it will be 1320 kilojoule. So this is the for heat engine case. Now what we have to do for this further? Here we found only W2 error. Now we have to go for the refrigerator. So COP refrigerator will be T4 minus T3 divided by T4, that you can add 253 divided by 300 minus 253, that is 5.38. Okay, now COP reference, you can refrigerator, you can write it as Q4 divided by W2. So from there Q4 you can write it as COP refrigerator times W2, it will be 5.38 times 1320, it will be 7101.6 kilojoule. Okay, now heat transfer to the refrigerator, that will be Q4 7101.6 kilojoule. Now what we have to find? W2, you know, Q3 minus Q4. So that will be, from that Q3 will be 8421 kilojoule. Okay, now the net heat transfer to refrigerator, it will be Q4, that you can 7101.6 kilojoule. Net and heat transfer to the 27 degrees Celsius, how much it will be? Q2 plus Q3, that is equal to 780 plus 8421.6. So Q2 plus Q3, you will get the value 9201.6 kilojoule. So this will be the answer. We will go to the next problem, last problem today's session. So it will be a domestic food freezer maintained at temperature of minus 15 degrees Celsius. The ambient air temperature is 30 degrees Celsius. If heat leaks into the freezer at continuous rate of 1.75 kilojoule per second, what is the least power to the pump this heat out continuously? So here what you have to do, you have to calculate the what is the least power. Now for that, T2 is given minus 15 degrees Celsius, so it will be 258 Kelvin. Then similarly T1 will be 30 degrees Celsius, so it will be 303 Kelvin. Okay, now Q2 value will be 1.75 kilojoule per second. Now you have to find the value of W. So COP of refrigerator, it's given Q2 divided by W, that we can write as T2 divided by T1 minus T2. So it will be 258 divided by 303 minus 258. So your answer will be 5.733. Okay, now this you can equate. W we can write it as Q2 divided by COP of refrigerator. So it will be 1.75 divided by 5.733. So your answer will be 0.3052 kilowatt. this problem you please note and solve for next class. Okay, please note down this problem.
Yes, ma'am.
I hope you noted it right.
Yes, ma'am. Taken.
Yeah. So now what we had, so we are stopping the session today here. Today we discussed only the heat pump and heat refrigerator, how it combine both, like output from the heat pump in heat engine goes to the heat pump or refrigerator. Okay, so related problem. So for each kind of every problem, you have to first do the diagram, then solve it. Then it will be easy. Okay.
Yes, ma'am.
Yeah.
Thank you, ma'am.
Yeah.
Thank you, ma'am. Thank you.
Yes, yes, yes. So
Monday I will there, ma'am.
yeah. So next Monday we'll meet you. Okay. Bye.
Yes, ma'am. Yes, ma'am. Good.